close your eyes for just a moment. Imagine you're standing in a garden at twilight. The air is cool against your skin. Above you, the first stars are beginning to pierce through the deepening blue of the evening sky. You reach out your hand to touch a flower, a delicate rose perhaps, its petals soft as silk. You can feel it, solid, real, there. But what if I told you that flower isn't quite as solid as it seems? What if I told you that you, your hand, your body, the very thoughts moving through your mind right now, are made of something far stranger than matter, something that flickers in and out of existence, something that can be in two places at once, something that only becomes real when you look at it? Welcome, dear traveler, to the Midnight Explorer. I'm so glad you're here, settling in for the night, perhaps with a warm drink in your hands or maybe just the comfortable weight of blankets around you. Tonight, we're going on a journey together. Not through space, though we'll touch the stars, and not through time, though we'll meet the greatest minds who ever lived. Tonight, we're journeying into something deeper, something that exists beneath the surface of everything you've ever known. We're going to explore the quantum world. And I promise you, by the time you drift off to sleep tonight, you'll never look at reality quite the same way again. But not the beginning, not the Big Bang, not the birth of stars. We're starting somewhere more intimate, more human. We're starting in the year 1900, on the edge of a new century, in a world that thought it had figured everything out. Picture, if you will, a winter evening in Berlin. The gas lamps are lit along the cobblestone streets, casting pools of golden light through the falling snow. Horse-drawn carriages clatter past, their wheels leaving dark tracks in the white. In the windows of elegant townhouses, you can see families gathered around pianos, their voices rising in song. It's December 14th, 1900. In a lecture hall at the Prussian Academy of Sciences, a man named Max Planck is about to stand up and speak words that will shatter the universe as humanity understands it. But he doesn't know that yet. He's nervous, actually. He's 42 years old, with a thick mustache and kind eyes that crinkle at the corners, and he's about to present a mathematical formula that even he thinks might just be a trick, a convenient fiction, something that works on paper but couldn't possibly be true. But before we get to that moment, that pivot point in human history, we need to understand what the world believed before Planck stood up. At the turn of the 20th century, physics seemed complete, nearly wrapped up with a bow. Isaac Newton had explained how planets moved through space, how apples fell from trees, how the clockwork universe ticked along with perfect, predictable precision. James Clerk Maxwell had unified electricity and magnetism into one beautiful set of equations. Scientists could predict eclipses, calculate trajectories, understand the behavior of gases and liquids and solids. The universe, they believed, was like a grand machine. Wind it up and you could predict exactly how every gear would turn forever and ever. Given enough information about the present, you could calculate the future with perfect certainty. There was just this small problem. A tiny little thing called black-body radiation. Imagine a piece of metal in a forge. As it heats up, it glows, first a dull red, then orange, then yellow, then white hot. Scientists knew this happened. They could see it. But when they tried to calculate why it happened using the established laws of physics, they got nonsense. Their equations predicted that any heated object should give off infinite amounts of energy at short wavelengths. The universe, according to their math, should be floating with ultraviolet light. Everything should be exploding with radiation. But it wasn't. Clearly, the universe was doing something their equations weren't capturing. Max Planck was a man who loved order. His colleagues described him as precise, methodical, even rigid. He believed in the established laws of physics with almost a religious devotion. But he was also honest, and the numbers weren't working. So, on that December evening, in that lecture hall in Berlin, Planck proposed something radical, something he himself barely believed. What if energy didn't flow smoothly and continuously like water from a tap? What if it came in tiny, discrete packets, little bundles of energy like coins rather than liquid? He called these packets quanta. One quantum, two quanta, tiny, indivisible units of energy. It was just a mathematical trick, he thought, a way to make the numbers work. Energy couldn't really come in packets. That would be absurd. But the formula worked perfectly. His equation matched the experimental data exactly, describing how hot objects radiate energy at every temperature. It was beautiful, elegant, and according to everything Planck believed about the universe, impossible. He spent the next several years trying to prove himself wrong. He couldn't. Somewhere in that Berlin lecture hall, in the scratch of chalk on a blackboard, in an equation that even its creator didn't believe, the quantum world had announced itself. Not with a shout, but with a whisper. A small constant, Planck's constant, we call it now. Barely larger than nothing. But it was enough. Enough to crack open reality. Enough to show that underneath the solid, predictable world we live in, something stranger was happening. Something that would change not just physics, but philosophy. Not just how we understand matter, but how we understand existence itself. And the man who would truly hear that whisper, who would chase it down into the depths and return with treasures beyond imagining, he was at that moment 21 years old, working in a Swiss patent office, and he couldn't get a teaching job because his professors thought he was too cocky. His name was Albert Einstein.
Let's travel now from Berlin to Bern, Switzerland. The year is 1905. Close your eyes and picture a small apartment on Kramgasse Street, on the third floor of a building that still stands today. The rooms are cramped, filled with books stacked on every surface. Laundry hangs by the window. A young woman, Mileva, rocks a baby, trying to get him to sleep. And at a small desk by the window, hunched over papers covered in equations, sits a young man with wild, dark hair and eyes that seem to be looking at something beyond the walls of the room. Albert Einstein. 26 years old, father, husband, third-class technical expert at the Swiss Federal Office for Intellectual Property. By day, he reviews patent applications for electromagnetic devices. It's not what he dreamed of doing. He'd wanted to teach, to research, to be part of the academic world, but that world had closed its doors to him. Too unconventional, they said. Too quick to question authority. So here he is, examining other people's inventions, making enough money to survive. But at night he works on his own ideas. 1905 would become known as Einstein's miracle year. In that single year, while working full-time at the patent office, while caring for a young child, while living in that cramped apartment on Kramgasse Street, Einstein published 4 papers that would revolutionize physics. One explained Brownian motion, providing definitive proof that atoms existed. One introduced special relativity, showing that space and time were woven together, that nothing could travel faster than light, that time itself could stretch and compress. One contained the most famous equation in history, E equals mc squared, showing that matter and energy were two forms of the same thing. And one took Planck's quantum hypothesis seriously. Einstein had been thinking about light. Everyone knew light was a wave. It had to be. Thomas Young had proved it a century earlier with his double-slit experiment, showing that light creates interference patterns just like ripples on water. Maxwell's equations described light as electromagnetic waves. It was settled science. But Einstein, sitting in his apartment in Bern, was thinking about something called the photoelectric effect. Here's what happens. When you shine light on certain metals, they emit electrons. Makes sense. The light wave is giving energy to the electrons, knocking them loose. But here's the strange part. The brightness of the light doesn't matter. You can shine very dim light and still get electrons emitted, as long as the light is the right color. Blue light works. Dim blue light works. But bright red light? Nothing. Not a single electron. It was as if the light wasn't transferring energy continuously, like a wave. It was as if each electron was being struck by something discrete, something particle-like. And the color of the light determined how much energy each strike delivered. Einstein took Planck's idea, energy in packets, and made it physical, real. He proposed that light itself came in quanta, little particles of light, each carrying a specific amount of energy determined by its frequency. He called them light quanta. Today we call them photons. Think about that for a moment. The light streaming through your window right now, the glow of your screen, the stars in the night sky, it's not a smooth wave washing over you. It's a storm of tiny particles, billions upon billions of them, each one discrete, each one whole unto itself, peppered across space like rain. But here's where it gets truly strange. Light is also a wave. Young's double-slit experiment proved that. And that experiment still works. Light still creates interference patterns. So what is light? A particle or a wave? Einstein's answer? Yes. Both. Somehow, impossibly, both. This was the first hint that the quantum world doesn't play by the rules we're used to. In our everyday world, something is either a particle or a wave. A baseball is a particle. It exists in one place at one time. A ripple on a pond is a wave. It spreads out. It interferes with other waves. It doesn't have a single location. But light, Einstein suggested, was both. And if light could be both, what about everything else? Einstein's paper on the photoelectric effect won him the Nobel Prize. Not his work on relativity, which most people still didn't understand or believe, but this paper, this quantum paper, was convincing. It made predictions. Those predictions were tested. They were right. The quantum world was revealing itself, piece by piece. But Einstein himself was beginning to feel uneasy. He'd helped birth this strange new physics. But as it grew, as others took his ideas further and further, he began to suspect he'd opened a door to something he didn't like, something that violated his deepest beliefs about how reality worked. But we're getting ahead of ourselves. First, we need to meet a young man in Denmark, sitting in his professor's laboratory, thinking about atoms, thinking about how electrons orbit a nucleus like planets around a sun, and realizing that, according to the established laws of physics, atoms shouldn't exist at all. It's 1911. Let's travel to Manchester, England, to the laboratory of Ernest Rutherford, a brilliant, boisterous New Zealander with a walrus mustache and a booming voice that, it was said, could curdle milk at 20 paces. Rutherford has just made a stunning discovery. For centuries, people thought atoms, if they existed at all, were solid, indivisible little billiard balls. But Rutherford has been firing alpha particles, tiny, positively charged bits of matter at thin sheets of gold foil, and most of them pass right through. Most. But some, a very few, bounce back, as if they've hit something incredibly small and incredibly dense. Rutherford realizes atoms aren't solid at all. They're mostly empty space. At the center sits a tiny nucleus, dense and positively charged. And around it, somehow, orbit the electrons, like planets around a sun. It's a beautiful picture, elegant, easy to visualize. And according to physics, it's impossible. Here's why. If electrons really are orbiting the nucleus, they're constantly accelerating, changing direction as they curve around. And according to Maxwell's equations, any charged particle that accelerates must emit electromagnetic radiation, must give off energy, which means the electron should spiral inward, radiating energy as it goes, and crash into the nucleus in about 100 millionth of a second. Every atom in the universe should collapse immediately. The world should not exist, but it does. You exist. The stars exist. This impossibility is everywhere, stable and real. Enter Niels Bohr. Picture him. A tall, gentle Danish man with a soft voice and a pronounced accent that makes it difficult to understand even in his native language. He's only 26 years old when he arrives at Rutherford's laboratory as a postdoctoral researcher. He's shy. He mumbles. His English is terrible. But inside his mind, something remarkable is happening. Bohr is thinking about hydrogen, the simplest atom, just one electron orbiting one proton. When you heat hydrogen gas, it glows with a very specific set of colors, not a smooth spectrum like a rainbow, but discrete lines: red, blue-green, violet, ultraviolet. Scientists had measured these lines with incredible precision. They even had a formula that predicted them. But no one knew why these particular colors appeared. Bohr, sitting in a library in Manchester, reading and thinking, has a wild idea. What if electrons can't orbit at just any distance from the nucleus? What if there are only certain allowed orbits, specific distances, specific energies? And what if electrons can only jump between these allowed orbits, absorbing or emitting a photon, one of Einstein's light quanta, when they do? Each jump would produce light of a specific color. The exact color would depend on the energy difference between the orbits. And if there are only certain allowed orbits, then you'd get only certain allowed colors. Discrete lines, specific wavelengths, exactly what the experiments showed. Bohr calculated. He used Planck's constant, that tiny number that even Planck thought was just a mathematical convenience. He built a model of the hydrogen atom with quantized orbits. And when he calculated what wavelengths of light his model would predict, they matched perfectly. Every single spectral line of hydrogen explained by this young Danish physicist mumbling to himself in a Manchester library. But here's the thing. Bohr couldn't explain why only certain orbits were allowed.
Our story now takes us to Paris, 1923. Louis de Broglie is 31 years old, and he's finally getting around to finishing his PhD. This isn't typical. Most physicists finish their doctorate in their mid-20s, but Louis isn't a typical physicist. He's a prince, for one thing, from one of the oldest noble families in France. His full title, if you want to know, is Louis Victor Pierre Raymond, 7th Duc de Broglie. He grew up in elegant mansions, learning history and the classics. His older brother Maurice was a physicist, and Louis initially studied history himself. But something about physics captivated him: the deep questions, the strange beauty of the laws underlying reality. World War I interrupted his studies. He served as a radio operator, spending years maintaining and operating wireless equipment in the Eiffel Tower. There, surrounded by electromagnetic waves, perhaps The seeds of his great idea were planted. After the war, he returned to his studies. And sitting in his Parisian apartment, thinking about Einstein's photons, thinking about Bohr's electron orbits, he asked himself a simple question. If light, which everyone thought was a wave, can also be a particle, could particles also be waves? Let that question sit with you for a moment. You are made of particles. Atoms, electrons, protons, deuterons. Tiny, discrete things with position and mass. When you touch a table, your hand's atoms are pressing against the table's atoms. Solid against solid. Real. But what if you're also a wave? What if your electrons, the ones currently flowing through the neurons in your brain as you listen to these words, aren't just particles orbiting your atomic nuclei? What if they're also waves, spreading out, oscillating, interfering with each other? De Broglie proposed exactly that. Every particle, he suggested, has an associated wave. The wavelength depends on the particle's momentum. Fast particles have short wavelengths, slow particles have long ones. For everyday objects, like baseballs and people, the wavelength is so incredibly tiny that the wave nature doesn't show up. We just see the particle behavior. But for electrons, for atomic particles, their wavelengths are comparable to atomic sizes, which means the wave nature matters. It shows up. It's real. This idea explained Bohr's mysterious allowed orbits. If electrons are waves, then only certain orbits are stable, the ones where the wave fits perfectly around the nucleus, completing an exact whole number of wavelengths. Like a string on a guitar, only certain vibrations are stable, creating the specific notes you can play. Electrons aren't just in their orbits, they are their orbits. Standing waves wrapping around the nucleus, vibrating with specific frequencies, specific energies. When de Broglie submitted his thesis, his advisor Paul Langevin was perplexed. The mathematics was sound, but the idea was so strange. He sent it to Einstein, asking for his opinion. Einstein read it and wrote back immediately. He has lifted a corner of the great veil. High praise from the man who'd discovered relativity. But would de Broglie's matter waves turn out to be real, or just another mathematical fiction? The test came in 1927. Two American physicists, Clinton Davison and Lester Germer, were bouncing electrons off a nickel crystal. They were trying to study the crystal's structure, but they noticed something odd. The electrons bounced off at specific angles, creating a pattern. An interference pattern. The same kind of pattern you get when waves overlap and interfere with each other. Electrons, solid, discrete particles with mass and charge, were behaving like waves, just as de Broglie predicted. Think about this. Right now, in your body, in the device you're listening on, in everything around you, particles are being waves. The boundaries between them aren't sharp lines, but fuzzy probability clouds. An electron in your fingertip doesn't have a precise position. It exists as a wave spread out over space, with a probability of being here, a probability of being there. Only when something measures it, when something interacts with it in just the right way, does the wave collapse and the electron appear in one specific place. This is the quantum world revealing its deepest strangeness. Things don't have definite properties until they're measured. Reality is, in some sense, created by observation. But we're getting ahead of ourselves again. That part of the story, the measurement problem, the collapse of the wave function, the role of observation, that comes later, and that's where things get truly bizarre. For now, let's sit with this. Particles are waves. Matter is wave-like. You are made of vibrations, oscillations, probability distributions spread out across space. And the man who would capture all of this in one elegant mathematical framework, who would write down the equation that governs every quantum wave, he was about to arrive in Copenhagen, young and brilliant and cocky, ready to revolutionize physics yet again. It's January 1926. In the Swiss Alps, in the ski resort town of Arosa, a 38-year-old physicist named Erwin Schrödinger has retreated to a villa with his mistress. He's left his wife at home in Zurich. He's brought with him a box of pearls as a gift and a problem that's been bothering him for months. Schrödinger is already well established. He's a professor, respected, sophisticated. He has wide-ranging interests: philosophy, poetry, Eastern mysticism. He speaks multiple languages. He's charming, witty, and, by all accounts, quite the womanizer. But right now, in this alpine retreat, he's focused on physics, specifically on de Broglie's matter waves. If particles are waves, there should be a wave equation describing them, something like the equations that describe sound waves or water waves or electromagnetic waves. But what would that equation be? Schrödinger sets to work. He writes equations, crosses them out, tries again. He's looking for something that will reproduce Bohr's energy levels for hydrogen, something that will make sense of the quantum rules that had been accumulating ad hoc and piecemeal over the past quarter century. And somewhere in that alpine villa, over the course of a few intense weeks, he finds it. The Schrödinger equation. An equation so fundamental to quantum mechanics that it's often called the most important equation in physics after Newton's laws and Maxwell's equations. It looks deceptively simple, written in the compact notation physicists love. I h bar, d psi by dt, equals h hat psi. But contained in those symbols is the entire quantum world. Let me try to give you a sense of what this equation means, without drowning you in mathematics. The psi in the equation is called the wave function. It's a mathematical object that describes a quantum system, an electron, an atom, a photon, whatever you're interested in. The wave function contains all the information about the system, where it might be, how fast it might be moving, what its energy might be. Notice I keep saying might be. That's crucial. The wave function doesn't tell you where the electron is. It tells you where it might be with what probability. It's a wave of possibilities, of potential realities. The Schrödinger equation tells you how this wave function changes over time. It's a differential equation. It describes how psi evolves from moment to moment, how the probabilities shift and flow. When Schrödinger applied his equation to a hydrogen atom, something magical happened. Out popped Bohr's energy levels, automatically. Not as assumptions, but as natural solutions to the equation. The allowed orbits, the discrete energy levels, the spectral lines, all of it emerged from the mathematics. And not just for hydrogen. Schrödinger's equation worked for more complex atoms, for molecules, for systems Bohr's model couldn't handle. It was more general, more powerful, more fundamental. Schrödinger published his results in a flurry of papers in 1926. The physics community was electrified. Here, finally, was a comprehensive framework for quantum mechanics, an equation that could, in principle, describe any quantum system. Solve the Schrödinger equation, and you could predict the behavior of atoms, the formation of chemical bonds, the properties of materials. It was a triumph. But what did it mean? What was this wave function really? Was it a physical wave, like a water wave or a sound wave, or was it just a mathematical tool, a way of encoding our knowledge about probabilities? And what about measurement? Schrödinger's equation describes how the wave function evolves smoothly and deterministically over time. But when you actually measure a particle's position, you find it in one place, not spread out as a wave. The wave function somehow collapses from many possibilities to one reality. How does that happen? When does it happen? The equation doesn't say. Schrödinger himself struggled with these questions. He'd created the equation, but even he wasn't sure what it meant. He hoped that the wave function was real, physical, that electrons really were spread out waves, and the apparent particles we see were just concentrated wave packets. But that interpretation led to problems of its own, because the wave function exists not in ordinary three-dimensional space, but in a much more abstract, higher-dimensional space. For a single electron, fine, the wave function can be visualized as a wave in normal space. But for 2 electrons, the wave function exists in 6 dimensions. 3 electrons, 9 dimensions. The wave function for a system of n particles exists in 3n dimensions, a space too abstract to visualize, too removed from everyday reality to feel physical. So what was the wave function? A real thing? A calculation tool? Something in between. Meanwhile, across Europe, another young physicist was developing a completely different formulation of quantum mechanics, one that looked nothing like Schrödinger's wave equation, one that was based on matrices and algebra rather than waves and calculus. And when physicists compared the two approaches, they found something astonishing. They were mathematically equivalent. Different languages, same underlying reality. The quantum world, it seemed, could be described in multiple ways, and no one was sure which way, if any, corresponded to how reality really worked. Let's rewind a bit, back to 1925, and meet someone extraordinary. Werner Heisenberg is 23 years old. 23. An age when many people are just finishing university. But Heisenberg already has his PhD, and he's already making revolutionary contributions to physics. He's intense, this young German. Athletic. He loves hiking in the mountains, often going on solo expeditions where he thinks about physics while climbing. He plays piano beautifully, with a particular love for Bach. And he has a mind like a steel trap, capable of holding vast amounts of mathematics and following logical chains to their conclusions with ruthless precision. In the spring of 1925, Heisenberg is struggling. He's been working on understanding atomic spectra, those discrete lines of color that atoms emit, using a new theoretical framework. But the mathematics keeps getting tangled. Nothing is quite working. Then, in June, a terrible bout of hay fever strikes him. His face swells up. He can barely see. It's so bad that his supervisor sends him away from the Pollenfield mainland to Heligoland, a bare, rocky island in the North Sea. There, alone, with nothing to do but recover and think, Heisenberg has a breakthrough. He realizes he's been thinking about the problem wrong. He's been trying to describe electron orbits, the paths electrons take around the nucleus. But those paths are unobservable. You can't actually watch an electron orbit. All you can observe are the transitions, an electron jumping from one energy level to another, emitting or absorbing light. So why not build a theory based only on what you can observe? Forget the orbits. Focus on the transitions, the energies, the probabilities of jumping from one state to another. Heisenberg starts writing down arrays of numbers, tables representing all the possible transitions between energy levels. Each number represents the probability amplitude of a particular transition. He develops rules for manipulating these tables, how to combine them, how to calculate with them. The mathematics is strange. When you multiply two tables, the order matters. A times B doesn't equal B times A. This is weird. In ordinary arithmetic, 3 times 5 equals 5 times 3. But Heisenberg's tables don't commute. They're fundamentally different depending on the order you multiply them. Heisenberg doesn't fully understand the mathematics he invented, but he applies it to the hydrogen atom, and it works. It predicts the right energy levels, the right spectral lines, all of it emerged from the mathematics. And not just for hydrogen. Heisenberg's equation worked for more complex atoms, for molecules, for systems Bohr's model couldn't handle. It was more general, more powerful, more fundamental. Born and his assistant, Pascal Jordan, work with Heisenberg to develop the theory fully. They create a complete, self-consistent formulation of quantum mechanics based on matrices. It's powerful. It's elegant in its own way. And it's almost impossible for anyone who's not a mathematical physicist to understand. Matrices? Abstract tables of numbers? Where are the nice visualizable waves? Where's the physical intuition? When Schrödinger publishes his wave equation a few months later, many physicists breathe a sigh of relief. Finally, something they can picture. Waves make sense. Waves are physical. The two approaches, Schrödinger's wave mechanics and Heisenberg's matrix mechanics, are used for different purposes. Wave mechanics for problems where you can think about spatial distributions. Matrix mechanics for problems where you're calculating transitions and probabilities. Then in 1926, Schrödinger proves that the two formulations are mathematically equivalent. They're different.
Picture Heisenberg in Copenhagen, working at Bohr's Institute. It's late at night. He's taking a walk through the snowy streets, thinking about gamma-ray microscopes. Stay with me here, this is important. If you want to see where an electron is, you need to bounce light off it. That's how vision works. Light reflects off objects and into your eyes. To see something very small, you need very short wavelength light, because the resolution of your measurement depends on the wavelength. To see an electron precisely, you need gamma rays, high-energy, short wavelength light. But here's the problem. Light is made of photons, and Einstein showed that photons carry momentum. When a gamma-ray photon bounces off an electron, it transfers some of its momentum to the electron. It gives the electron a kick, a big kick, because gamma rays are high energy. So by measuring the electron's position precisely, you've changed its momentum. The very act of observation has altered what you're observing. Heisenberg sits down and calculates. How precisely can you know both the position and the momentum of a particle? And he discovers a profound limit encoded in a simple inequality. Delta x times delta p must be greater than or equal to a tiny number, half of Planck's constant. This isn't a statement about measurement error. It's not saying our instruments aren't good enough. It's saying that the universe itself doesn't allow particles to have both a definite position and a momentum simultaneously. If you know exactly where a particle is, delta x equals 0, then its momentum is completely uncertain, delta p equals infinity. If you know exactly how fast it's moving, delta p equals 0, then its position is completely uncertain, delta x equals infinity. There's a trade-off, a fundamental, irreducible fuzziness to reality. This is so important, so central to our story that I want you to really feel it. Let me give you an example. Imagine trying to take a photograph of a hummingbird. If you use a very short shutter speed, a quick flash, you can capture exactly where the hummingbird is at that instant. The image is sharp, clear. But because the exposure is so brief, you can't tell how fast the bird was moving. The motion is frozen, information about velocity lost. Now imagine using a long exposure. The hummingbird becomes a blur, a streak across the frame. Now you can see the motion, the direction, the speed. But where exactly was the bird? The position is smeared out, uncertain. That's analogous to what Heisenberg discovered, except it's not a limitation of cameras, it's a limitation of reality itself. An electron doesn't have both a position and a momentum, not because we can't measure them, but because those properties don't exist simultaneously in the quantum world. The electron exists in a state where position and momentum are both fuzzy, both probabilistic,
both spread out. The uncertainty principle applies to other pairs of properties too. Energy and time, for instance. If you want to know exactly what energy a particle has, you need to observe it for a long time. If you want to know exactly when something happened, the energy becomes uncertain. This has real, observable consequences. It means that even in empty space, in a perfect vacuum, particles can pop into existence for brief moments, borrowing energy from the universe as long as they disappear again quickly enough that the energy-time uncertainty relation isn't violated. Empty space isn't empty. It's seething with quantum fluctuations, with virtual particles appearing and disappearing, with a restless energy that pervades everything. This vacuum energy is real. We can measure it. It causes forces between metal plates placed close together in vacuum, the Casimir effect. It causes slight shifts in atomic energy levels, the Lamb shift. The universe's emptiness is full of quantum activity. But let's return to the deeper meaning of uncertainty. What Heisenberg had discovered wasn't just a practical limit on measurement. It was a statement about the nature of reality itself. In the classical world, the world of Newton and Maxwell, the world we experience in our daily lives, objects have definite properties. A baseball has a position and a velocity at every moment. Even if we don't measure them, they exist. The baseball is somewhere, moving at some speed, whether we look or not. But in the quantum world, properties don't exist independently of measurement. An electron doesn't have a position until you measure its position. It doesn't have a momentum until you measure its momentum. Before measurement, it exists in a superposition, a quantum state that's a blend of all possibilities. This was disturbing, deeply disturbing to many physicists, including some who had helped create quantum mechanics. Einstein, in particular, hated it. He believed in an objective reality, a universe that exists independent of observation, with definite properties whether or not anyone is looking. In 1927, the world's leading physicists gathered in Brussels for the Solvay Conference, and there, Einstein and Bohr began a debate that would last for the rest of their lives. A debate about the nature of reality itself. The photograph from the 1927 Solvay Conference is one of the most famous images in science. 29 people, the greatest minds in physics, seated and standing in formal poses. Einstein is there, in the front row, his hair already wild and white, though he's only 48. Bohr is beside him, serious and contemplative. Marie Curie is there, the only woman in the photo, and one of only 5 women who attended the conference. Heisenberg, Schrödinger, de Broglie, Born, Planck, all the architects of quantum mechanics gathered in one room. But beneath the formal poses, a battle is raging. The topic of the conference is electrons and photons, basically quantum mechanics and what it means. Most of the physicists there have accepted the new theory. The mathematics works, the predictions are confirmed. Quantum mechanics is successful. But what does it mean? Bohr has developed what becomes known as the Copenhagen interpretation. It's not really a single unified interpretation, more a set of ideas and attitudes about how to think about quantum mechanics. But its core claims are radical. 1. The wave function is all there is. It contains complete information about a quantum system. There's no hidden reality underneath it, no deeper level where particles have definite positions and momenta. 2. Properties don't exist until they're measured. Before measurement, a particle exists in a superposition of all possible states. The act of measurement causes the wave function to collapse to one definite outcome. 3. Complementarity. Some properties, like position and momentum, are complementary. You can measure one or the other, but not both precisely. Particles have a wave nature and a particle nature, and which one you see depends on what kind of experiment you do. 4. You can't ask what the particle is really doing between measurements. That question is meaningless. Quantum mechanics tells you how to calculate probabilities for measurement outcomes, and that's all physics can do. The rest is metaphysics, philosophy, not science. Einstein finds this interpretation abhorrent. God does not play dice with the universe, he tells Bohr. It's become his most famous quote about quantum mechanics, though what he means is often misunderstood. Einstein isn't objecting to probability per se. He knows that sometimes we use probabilities because we don't have complete information. When you flip a coin, you use probability because you can't track every air current and muscle twitch. But the coin itself has a definite state at every moment. The randomness is in your knowledge, not in reality. Quantum mechanics, according to Bohr, says the randomness is fundamental. Before you measure an electron's position, it doesn't have one. It's not that you don't know where it is, it's that where it is isn't a meaningful concept. The electron exists in a superposition of being in many places at once. Einstein can't accept this. He believes in realism, the idea that the universe has definite properties independent of observation. He believes in locality, the idea that objects are only directly influenced by their immediate surroundings, not by distant events. And he believes that quantum mechanics, as successful as it is, must be incomplete. There must be deeper variables hidden from us that determine the outcomes of quantum measurements. The apparent randomness is just our ignorance of these hidden variables. Every morning at breakfast during the conference, Einstein proposes a thought experiment, an imaginary device or scenario that would, he claims, allow you to violate the uncertainty principle or otherwise show that quantum mechanics is inconsistent or incomplete. And every evening, Bohr comes back with a detailed analysis showing why Einstein's thought experiment doesn't work, how quantum mechanics accounts for everything, how the uncertainty principle survives intact. Bohr later said these discussions with Einstein were among the most profound intellectual experiences of his life. Einstein wasn't just quibbling over details. He was probing the deepest questions. What is reality? What can we know? What does it mean to say something exists? Picture them, these two giants, walking through the streets of Brussels, arguing passionately. Einstein with his thought experiments, trying to find a crack in the quantum edifice. Bohr with his careful analysis, defending the consistency of the new physics. They're not enemies, they respect each other deeply, but they fundamentally disagree about the nature of reality. Years later, in 1935, Einstein would make his most famous attack on quantum mechanics. Working with two younger colleagues, Boris Podolsky and Nathan Rosen, he published a paper titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" The paper is usually known by the initials of its authors, EPR. The EPR paper describes a thought experiment involving two particles that have interacted and then separated. According to quantum mechanics, these particles can be in an entangled state. A single wave function describes both particles together, even when they're far apart. Now, here's the strange thing. If you measure a property of one particle, say its position, the wave function collapses and instantly the other particle has a definite value for the corresponding property. even if the two particles are on opposite sides of the galaxy. Einstein, Podolsky, and Rosen argued that either 1. The measurement on one particle somehow instantly affects the other particle, even across vast distances, which would violate locality, the principle that objects can only be influenced by their immediate surroundings, or 2. Both particles had definite properties all along, and quantum mechanics is simply incomplete. It doesn't describe these elements of reality. Einstein preferred option 2. Quantum mechanics works, but there's a deeper level of reality it doesn't capture. There essentially was that Einstein was still thinking classically. In the quantum world, the two particles aren't really separate after they interact. It's not that measuring one particle affects the other across space, it's that the very idea of them being separate, independent entities is wrong. The debate seemed philosophical, abstract, a matter of interpretation. But decades later, physicists would discover that it was more than that. The debate between Einstein and Bohr had testable consequences. And when the tests were done, well, we'll get to that. First, we need to meet the shy, chain-smoking Irish physicist who asked a question no one thought to ask. What if quantum mechanics is wrong?
John Stuart Bell was born in Belfast, Northern Ireland, in 1928. His family wasn't wealthy. His father was a horse dealer, not an academic. But young John showed exceptional mathematical talent and eventually made his way to university, then to graduate school. He became a particle physicist, working on accelerator design and quantum field theory. But in his spare time, he thought about foundations, about what quantum mechanics really means, about the Einstein-Bohr debate, about whether there could be hidden variables underneath quantum mechanics. Most physicists didn't think about these questions. By the 1950s, quantum mechanics was established, successful, useful. It worked. Who cared about interpretation? Shut up and calculate, as one physicist quipped. But Bell cared. He was bothered by the measurement problem, the fact that quantum mechanics treats measurement as something special, something that causes wave function collapse, but doesn't explain what constitutes a measurement or why it should have this special role. He was sympathetic to Einstein's view. He wanted there to be a deeper reality underneath the quantum probabilities. In 1964, Bell was spending a sabbatical year away from his usual work, and he decided to tackle the EPR problem seriously. Not philosophically, but mathematically. He asked, could there be a hidden variable theory, a deeper description of reality that reproduces all the predictions of quantum mechanics, but restores realism and locality? And he discovered something shocking. Bell proved a theorem, now called Bell's theorem, that showed no local hidden variable theory can reproduce all the predictions of quantum mechanics. Let me say that more carefully, because it's subtle and profound. Bell showed that if you assume, 1, realism, particles have definite properties independent of measurement, and 2, locality, measuring one particle can't instantly affect another distant particle, then you get predictions that differ from quantum mechanics. Specifically, he derived an inequality, Bell's inequality, that any local realistic theory must satisfy. And quantum mechanics violates this inequality. This was extraordinary. The debate between Einstein and Bohr wasn't just philosophical, it was testable. You could do an experiment, measure certain correlations between entangled particles, and check whether nature obeys Bell's inequality. If it does, Einstein was right. Quantum mechanics needs to be supplemented with hidden variables. If it doesn't, then something has to give. Either realism is false, particles don't have definite properties before measurement, or locality is false. Measuring one particle really does instantly affect another distant particle. Or both. Bell himself was surprised by his result. He'd hoped to vindicate Einstein, to show that hidden variables could work. Instead, he'd shown that either quantum mechanics is wrong, or our intuitions about reality and locality are wrong. The question now was,
What does nature actually do? The experiments were difficult. To test Bell's inequality properly, you need to create pairs of entangled particles, send them to distant detectors, measure them in different ways, and look at the correlations. You need to do this thousands or millions of times to get good statistics, and you need to close various loopholes, ways the experiment could give misleading results. The first experiments were done in the early 1970s by John Clauser and Stuart Friedman. They used entangled photons and measured their polarizations. The results? Violated Bell's inequality. Nature disagreed with local realism. Quantum mechanics was right. More experiments followed. In 1982, Alain Aspect in France did a more sophisticated version, closing some of the loopholes. Same result, violation of Bell's inequality. Experiment after experiment, over decades, with increasing precision and fewer loopholes, all confirmed the same thing. Nature exhibits quantum correlations that cannot be explained by any local realistic theory. What does this mean? It means that Einstein, for all his genius, was wrong about this one. The universe doesn't work the way he thought it should. Quantum entanglement is real. When two particles are entangled, measuring one really does have an immediate correlation with the other, no matter how far apart they are. It's not that information travels faster than light. You can't use entanglement to send messages, but the correlations are there, stronger than any local realistic theory allows. The universe, at its deepest level, is non-local. Things that are far apart can be connected in ways that transcend space. Or, alternatively, realism is false. Properties don't exist until they're measured. The universe doesn't have definite states independent of observation. Most physicists lean towards giving up realism rather than locality, but the philosophical implications, either way, are profound. Bell himself remained troubled by quantum mechanics until his death in 1990. He felt the theory was still missing something, that the measurement problem wasn't solved just by accepting non-locality or giving up realism. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments testing Bell's inequalities and establishing the reality of quantum entanglement. Bell himself never won the Nobel Prize. He died too young, and the prize isn't awarded posthumously. But Bell's theorem is one of the most important results in all of physics. It showed that the weirdness of quantum mechanics isn't just in our heads, isn't just a matter of interpretation. It's in nature itself. The quantum world is strange, provably, testably, undeniably strange. We need to talk about the cat. You've probably heard of it, Schrödinger's cat, the most famous feline in physics, a cat that's both alive and dead at the same time, trapped in a box with a quantum poison device. But do you know why Schrödinger proposed this thought experiment? What point he was trying to make? It wasn't to explain quantum mechanics, it was to show how absurd quantum mechanics seemed when you tried to apply it to everyday objects. Let's set the scene. It's 1935. Schrödinger is reading the EPR paper, Einstein's attack on quantum mechanics. Schrödinger is sympathetic to Einstein's concerns. He's the one who wrote down the wave equation, yes, but he's increasingly troubled by what it seems to imply. So he writes an essay exploring the strangeness of quantum mechanics, and in it, he proposes this thought experiment. Imagine a cat, sealed in a box. Inside the box is a vial of poison, a hammer, a Geiger counter, and a tiny amount of radioactive material, just enough that over the course of an hour, there's a 50% chance one atom will decay. If the atom decays, the Geiger counter detects it, triggers the hammer, which smashes the vial, releasing the poison, killing the cat. If the atom doesn't decay, nothing happens, and the cat lives. Now, quantum mechanics says that before you observe it, the radioactive atom exists in a superposition of decayed and not decayed. It's both, simultaneously, until your measurement collapses the wave function to one outcome or the other. But the atom is connected to the Geiger counter, which is connected to the hammer, which is connected to the vial, which is connected to the cat. So if the atom is in a superposition,
then the entire system should be in a superposition, including the cat. Before you open the box and look, the cat is in a quantum superposition of alive and dead. Schrödinger found this absurd. He was making a reductio ad absurdum argument, showing that if you take the Copenhagen interpretation seriously and apply it to everyday objects, you get absurd conclusions. Obviously, he thought, the cat is either alive or dead inside the box, even before you look. It's not in some ghostly superposition of both. Quantum mechanics works for atoms and electrons, but somewhere between the atomic scale and the scale of cats, the quantum weirdness has to give way to classical definiteness. But where? When? How? This is called the measurement problem, and it's still not fully solved. Here's the deep question. When does a quantum superposition collapse into a definite state? Is it when a conscious observer looks? That seems absurdly anthropocentric, as if humans or consciousness has some special role in physics. Is it when the quantum system interacts with a large classical measuring device? But what counts as large enough? What counts as a measuring device? The Geiger counter? The hammer? Some specific number of atoms? Is it that superpositions never collapse, but the world branches into multiple realities, one where the cat is alive, one where the cat is dead, and we just experience one branch? This is the many worlds interpretation, which we'll come to. Or is it that quantum mechanics itself needs to be modified? Perhaps there's a new physical process, not yet discovered, that causes collapse when systems get big enough or complex enough. Modern research in quantum mechanics often focuses on decoherence, the process by which quantum systems lose their delicate superposition states when they interact with their environment. Here's the idea. In principle, the cat is in a superposition, but the cat is not isolated. It's interacting with air molecules, photons, vibrations, an environment with countless degrees of freedom. These interactions cause the phases of the superposition to randomize, washing out the quantum interference effects. Very quickly, the cat effectively becomes either alive or dead from any practical standpoint, even though there is no true wave function collapse. Decoherence explains why we don't see quantum superpositions in everyday life.
Let's talk about something miraculous, something happening right now as you listen to these words, something that keeps you alive, that makes possible every breath you take, every thought you think. The sun is shining. That might not sound miraculous. The sun shines every day. But the fact that it shines at all, that nuclear fusion can happen inside the sun's core, is only possible because of quantum mechanics. Let me explain. The sun generates energy by fusing hydrogen nuclei, protons, into helium. 4 protons come together through a series of reactions to form one helium nucleus. The helium weighs slightly less than the 4 protons did. That missing mass becomes energy via Einstein's E equals mc squared. That energy radiates outward, eventually reaching Earth as sunlight. Fusion. Simple enough in concept. But here's the problem. Protons are positively charged. Like charges repel. If you try to push 2 protons together, they push back with tremendous force. The closer you bring them, the stronger the repulsion. To overcome this repulsion, to get the protons close enough that the strong nuclear force can grab them and fuse them together, you need enormous energy. In human-built fusion reactors, we heat hydrogen to hundreds of millions of degrees. But the sun's core, while hot, is only about 15 million degrees Celsius. According to classical physics, that's not nearly hot enough. The protons don't have enough energy to overcome their mutual repulsion. According to classical physics, the sun shouldn't shine. But it does, because quantum mechanics allows something impossible: quantum tunneling. Remember that particles are waves? The wave function of a proton extends through space as a probability distribution. Most of the probability is concentrated in one region, where you'd classically expect to find the particle. But the wave function never goes exactly to zero. There's always a tiny tail, a fading probability extending outward. Now imagine a proton approaching another proton. Classically, it would bounce off the energy barrier created by electrical repulsion, like a ball rolling up a hill. It doesn't have enough energy to reach the top, so it rolls back down. But quantum mechanically, the proton's wave function extends slightly into the barrier and even through it. There's a small but non-zero probability that the proton can appear on the other side of the barrier, inside the range where nuclear forces dominate. It's as if the ball rolled up the hill, couldn't reach the top, but suddenly appeared on the other side. It tunneled through. This isn't just theory. We can measure quantum tunneling in laboratories. It's real. And in the sun, it happens constantly. Protons tunnel through the electrical repulsion barrier, get close enough to fuse, and release energy. The sun shines because of quantum tunneling. Think about that. Every photon of sunlight that has ever warmed your face, every ray that has nurtured every plant, every bit of solar energy that has driven the climate and the weather and the evolution of life on Earth, all of it is possible because particles can do something classically impossible. Because the quantum world allows probabilities where the classical world allows only certainties. Because reality is, at its deepest level, probabilistic. Quantum tunneling shows up in other places too. It's why alpha particles can escape from radioactive nuclei. They tunnel through the nuclear forces that should contain them. It's how scanning tunneling microscopes work. They measure the tiny current of electrons tunneling from a surface to a needle-sharp probe, allowing us to image individual atoms. It's involved in how enzymes work in your body, speeding up chemical reactions that would otherwise be too slow to sustain life. It's possibly involved in how birds navigate using Earth's magnetic field. There are hints that quantum effects in proteins in birds' eyes allow them to see magnetic fields. The quantum world isn't some distant, abstract realm. It's not confined to physics laboratories. It's here, everywhere, underlying everything. Without quantum mechanics, there would be no fusion in stars. Without fusion in stars, there would be no heavy elements, the carbon, oxygen, nitrogen that make up your body. Without quantum mechanics, there would be no chemistry as we know it, because the behavior of electrons in atoms is purely quantum. You are quantum mechanical, made of quantum particles held together by quantum forces, alive because of quantum processes. The miracle is that the classical world exists at all, that big collections of quantum particles behave in predictable, non-weird ways. That's the emergence of classicality from quantum foundations. And it's one of the things physicists still work to understand fully. Let's journey now to the present day and glimpse the future. For most of the 20th century, quantum mechanics was something physicists used to understand nature, to explain why atoms have the properties they do, why materials behave as they do, why the sun shines. But in the last few decades, we've started to do something new. We've started to engineer quantum systems, to deliberately create and manipulate quantum states, to build technologies that don't just rely on quantum mechanics passively, but actively exploit quantum weirdness, superposition, entanglement, tunneling, to do things impossible with classical physics. Quantum technologies are no longer science fiction. They're here, developing rapidly, promising to transform computing, cryptography, sensing, and more. The most famous quantum technology is the quantum computer. A classical computer processes information in bits, ones and zeros. Each bit is definite. It's either 1 or 0 at any given moment. A computer with n bits can be in one of 2 to the n possible states, but only one state at a time. A quantum computer uses quantum bits, or qubits. And a qubit, because it's quantum, can be in a superposition of 0 and 1 simultaneously. 2 qubits can be in a superposition of all 4 possible states, 0, 0, 0, 1, 1, 0, 1, 1, all at once. 3 qubits can represent 8 states simultaneously. N qubits can be in a superposition of 2 to the n states simultaneously. This is called quantum parallelism. A quantum computer with just 300 qubits could, in some sense, be exploring 2 to the 300 possibilities at once, a number larger than the number of atoms in the observable universe. Now, it's not quite as simple as we can try every possible answer at once and pick the right one. Quantum computing doesn't work that way. The challenge is designing algorithms that use superposition and interference to amplify the probability of the correct answer while canceling out wrong answers. But for certain problems, this works stunningly well. Peter Shor, in 1994, discovered an algorithm that allows a quantum computer to factor large numbers exponentially faster than any known classical algorithm. This is important because much of modern cryptography relies on the difficulty of factoring. It's easy to multiply 2 large prime numbers, but hard to factor the result back into primes. A large enough quantum computer running Shor's algorithm could break most current encryption. It's not an immediate threat. We don't yet have quantum computers large and stable enough, but it's coming. Governments and companies are already developing post-quantum cryptography, encryption methods that even quantum computers can't crack. Love Grover discovered an algorithm for searching unsorted databases that gives a quadratic speedup, not as dramatic as Shor's, but still significant. And researchers are discovering more quantum algorithms, finding problems where quantum computers have advantages, simulating other quantum systems, which is useful for chemistry and material science, optimizing complex systems, machine learning tasks, and more. Building quantum computers is extraordinarily difficult. Qubits are delicate. They need to be isolated from their environment because any interaction causes decoherence. The quantum superposition degrades, and your qubit starts behaving classically. Different approaches are being tried: superconducting qubits cooled to near absolute zero, ions trapped in electromagnetic fields and manipulated with lasers, neutral atoms held in optical lattices, photons traveling through optical circuits, defects in diamond crystals, and more. Each approach has advantages and challenges. It's an active, exciting field of research. As of now, we have quantum computers with dozens to hundreds of qubits. Google claimed quantum supremacy in 2019, demonstrating a computation that would be impractical on classical computers, although the practical usefulness of that particular computation is debated. The race is on to build larger, more stable, error-corrected quantum computers that can tackle real-world problems.